Okay, now we're going to start looking at some other parts of rational functions, namely the zero and the intercepts and the wholes of rational functions. So if you recall the domain of a rational function, the domain of a rational function, we'll say f of x equals p of x over q of x is all real numbers except those x where q of x is equal to 0. We want to eliminate everything that makes the denominator 0. So these things that make the denominator 0, they are not useless. They actually do lots and lots and lots of things. One thing, these things that make the bottom 0, sometimes they create what are called wholes or singular points of discontinuity, also sometimes referred to as a removable discontinuity. So a hole in a graph will look something like this, where we have a graph just kind of going along, and then at some point it has a gap in the graph, which we typically signify with an open circle, and then the graph continues doing whatever it is. So this gap here you see is called a hole. Now on a graphing calculator, these holes are not very easy to see, but we kind of signify it on a handmade graph with this open circle. So a hole is simply going to be a single point or a single gap in the graph of a function. And with rational functions, these are really, really easy to see. So in rational functions, where do we see these? These always appear at any factor you cancel out. So any factor you cancel out will create a hole. So let's go ahead and look at an example. Let's say I had a random polynomial. Let's say I had f of x equal to x plus 2, x minus 1, x plus 2. Now the domain of this is all real numbers except for 1 and negative 2. But you can see this x plus 2 cancels to put it in lower terms. So because it canceled out, whatever made that factor 0 is going to create a hole. So this thing would have a hole at x equal to negative 2. So here's an example. It says, where do the following rational functions have holes? Verify on the graph of the function. So we have f of x equals x squared plus 5x plus 6, and we have 9 minus x squared. Now obviously, what I'd like to do is I'd like to factor it and see if anything cancels out. So if I factor the numerator, this factors as x plus 2, x plus 3, simply because two numbers that multiply to 6 that add to 5 are 3 and 2. The bottom is 9 minus x squared. That's our difference of squares. So if I factor that, I get 3 minus x and 3 plus x. So if I'm talking domain of this function, the domain would be all reals except for 3 and negative 3. And remember, we always do the domain before we cancel out. And if I'm looking for factors that are the same, nothing looks exactly the same, but these two are the same because they're just switched in addition. And x plus 3 is the same as 3 plus x. So I can cancel those out. I can cancel those two factors out. So when you cancel out, that means we're going to create a hole. So there's a hole at x equal to negative 3. Now, if I wanted to see what the y value of this hole is, we certainly can, because our function now in lowest terms, our function is x plus 2 over 3 minus x. And so I can plug negative 3 in there, and I can get a value. If I plug in negative 3, even though it's undefined in the original function, in the lowest terms function it's not. So negative 3 plus 2 is negative 1. 3 minus negative 3 is 6. So you get negative 1, 6. So the hole occurs at negative 3, negative 1, 6. So on the graph at -3, -1, 6, you'd have an open circle. So this point really isn't on the graph, but this is kind of your open circle spot. So what I did to check this with the graph is I simply plugged my function into Desmos and I got this graph. So we kind of think our hole should be somewhere over here at 3 and -1, 6. -3 and -1, 6, somewhere like there, right? Now, Desmos doesn't show it, it just shows a continuous line, but the hole actually is there. What you can do is if you drag your mouse on the curve and you get very close to -3, at -3 it actually still will say -3, comma, undefined, which means it is non-existent there. What I also did is I made a table of values, and you can make a table of values in Desmos. If you click this little gearbox on your function, there is a function that says table. Looks like a couple columns and rows. If you click that, it brings up this table. And if you can see what happens at -3 where our hole is, you'll see where it says undefined. And once you pull up this table, you can change the values of that. So that's a really helpful function of this graphing calculator. So even if you can't see the hole per se on the graph, you certainly can get it from the table in conjunction with your algebra. So lots of ways to see the same thing in this problem. Okay, so let's look at one more example. We have g of x equal x cubed minus 2x squared minus 6x plus 12. Now this one's a little harder to factor because you have a cubic in the top. The bottom is relatively simple to factor. It's just a difference of squares. So it's going to be x minus 2x plus 2. Now as for the top, this goes back to what we talked about in chapter 2, where we're trying to find the zeros of this function so I can write it as a product of linear factors. So if I look at this, I can get possible rational zeros. So remember, the possible rational zeros are plus minus 1, plus minus 12, plus minus 2, plus minus 6, plus minus 3, plus minus 4. And so I'll just check in Desmos or a graphing calculator to see which of these actually are zeros. So which one actually turn out to be rational zeros from our graph. Now the only rational zero I see on Desmos is 2. Nothing else really works. So if I divide that out in Desmos, I get 2. 1, -2, -6, 12. 1, 2, 0, 0, -6, -12, and 0. So that was a third degree. I divided it once, so this is x squared minus 6. I certainly could figure out what that is, but I really don't care what it is, what the zeros of that are, because really what I care about are the rational ones, because I have x minus 2 and I have x squared minus 6. So the one thing that you see that cancels out, now if I want to list my domain again, that's never a terrible idea. So the domain again, all real numbers, x not equal to 2 and -2. But the negative x minus 2's are what cancels out. So it's going to create the hole is going to be at x equal 2. And so then if I wanted to find the y value, I could plug it into the lowest terms. I could plug in 2 into the function to see where it is. So if I look at my graph, we want to see, does the graph agree that there is a hole at 2? Or does it not agree? Now, if you look at it, the table I made is somewhat misleading. It says there is an undefined value at -2, which there is, but that's not a hole, because if you look at -2, this does not look like a single hole. Over here at 2 is where the single hole is. So what you should do on your Desmos is put 2 in, and hopefully it says undefined, because holes are not the only kind of undefined value. We'll see lots of other things that could be undefined. But for this, at least, make sure you check that, and it should show you that hole. But the algebra certainly lends to the fact that there is a hole at 2, because that is the factor that canceled out. So the other thing we're going to look at in this section is we found these holes, these kind of single points of discontinuity, these little single gaps in the graph. Another thing that's obviously very important to do on any kind of functional graph is to find intercepts. And so we talked about y-intercepts, so we'll kind of figure out how we can find those in a rational function. So y-intercepts, remember, is any point where the graph crosses the y-axis. And that's true for any function. And remember, it's always where x equals 0. So all we typically have to do is plug in 0 for a function and we can find their y-intercept. So y-intercepts are definitely the easiest to find. You plug in 0, you figure out what your value is, and that is what it is. It's really quite simple to find. X-intercepts, not quite as easy. So if we remember x-intercepts and 0, the first part, of course, x-intercepts are where the x-axis, or where the graph crosses the x-axis. And we could also say it's always where y equals 0. So it's where y, or f of x, equals 0. Okay? So we also remember there's another name. Remember, zeros of the function are always at the x-intercepts. So whatever the x-intercepts are also your zeros, because that's the number you'd plug in and get 0. Now for our functions that we're talking about, these rational functions, there's a really simple way to figure out where those are. So for rational functions, when we're trying to figure out where the x-intercepts and zeros are, all we have to look for is we want to look where the numerator is 0 in lowest terms. So we look where the numerator equals 0 when in lowest terms. So we want to get rid of those holes, and then in lowest terms, anything that makes the numerator 0 will make an x-intercepts. And the reason is because if you think of any fraction, if you think of a fraction 0 divided by any number, it's always 0. So in lowest terms, if you can get a 0 on top and anything else on the bottom, you always get a 0. Thus, you always get an x-intercept. So let's look at a couple examples of this. So this first one looks like this. It is 2x squared minus 7x plus 3x minus 7. We want to find the x and y intercepts, state the domain, and if there are any holes, state those as well. Verify with the graph of the function. And you can see I have the graph of the function here that you could certainly find in Desmos. I will mention the graph of this function is kind of incomplete here. We'll talk about that here in a second. But let's go ahead and factor this to see what we got. So we have x minus 7 on the bottom. And on the top, this factors is 2x and x. We're trying to unfoil it. No, however you learned unfoiling is fine. To factor this, 2x minus 1, x minus 3. You can check that by foiling. We get negative 6 minus 1, which is your negative 7x in the middle. If you have issues with factoring, you forget factoring, I think that's a good thing to look up on YouTube or a million other places where you can practice your factoring. So now, if I look at the domain, so the domain will start first. I always like to start with the domain. So it's all reals except 7. That's the only thing that makes the bottom 0. Now as far as holes, there are no holes because nothing cancels out. And most functions don't have holes because a lot of times they don't have these factors that cancel out. This one does not, so there's no hole. Now y-intercept, all we're going to do is we're going to plug in 0. So that's simply f of 0. Now you can plug into the factored form for y-intercept. You can plug into the original. It does not really matter. I'll plug into the original. 2 times 0 squared minus 7 times 0 plus 3 over 0 minus 7. So everything pretty much eliminates except for the 3 and negative 7. So I know there should be a y-intercept at 0 and negative 3/7. And if I look at the graph, I picked the dot that was the y-intercept, and you notice it's 0, negative 0.429. And if you check what the decimal equivalent of 3/7 is, you'll get the same thing. So now we just have to look for the x-intercepts, and actually we've done all the hard work for x-intercepts. Because remember, x-intercepts are just what makes the numerator equal to 0 when in lowest terms. It's already in lowest terms, it's already factored. So we're really just trying to figure out when is 2x minus 1 times x minus 3 equal to 0. And if you already have it factored, all you have to do is set those two factors equal to 0. 2x minus 1 equal to 0, x minus 3 equal to 0. So I add 1 divided by 2, I get half. I add 3, I get 3. So I should have an x-intercept at half 0 and 3, 0. And lo and behold, when I look at my graph on Desmos, I saw 3, 0, and I saw 0.50, just by clicking on the intercepts. So algebra is important, especially if Desmos gives you some irrational kind of 0 for the x-intercept. That's obviously very important, but the graphing calculator is a great way to check your work. Like I said, I did want to mention that there is more to this graph. It's kind of up here in this area, so if you zoom out, you'll actually see the rest of this graph that kind of looks like this. I just didn't want you to think this was all the graph looked like. There actually is more to this graph. Let's look at this last one. So we have g of x equals x squared minus 10x plus 21 to x squared minus 18. So first thing I'll do is factor. Top is pretty easy to factor. Two numbers that multiply to 21 add to negative 10 or negative 7, negative 3. The bottom, I can take a 2 out, so I have 2x squared minus 9. When I take a 2 out, always take out your GCF. And then I can factor the remaining as the difference of squares. So x minus 7, x minus 3 on top. 2, x minus 3, x plus 3 on bottom. So when I start looking for the things that I want in this problem domain, everything except for 3 and negative 3, because those are the x values that make the bottom 0. I do have one factor that cancels, the x minus 3. So I know there's going to be a hole at x equals 3. And since my lowest terms function now is x minus 7 over 2 x plus 3, I certainly can plug in 3 and figure out where that's going to be. So 3 minus 7 is negative 4. 2 times 3 plus 3 is 2 times 6, which is 12, which is negative 1/3. So the hole is somewhere going to be at 3, negative 1/3. Now remember, that is not a point on the graph. That's the missing point on the graph. But this would be our open circle on our graph. Y-intercept is the easy one. So y-intercept, we just plug in 0 for x. So we have g of 0. So at 0 squared minus 10 times 0 plus 21 over 2 times 0 squared minus 18. 21 over 18 both divide by 3, so that's 7 over negative 6. So we have a y-intercept of 0, negative 7, 6. So we know a gap in the graph, and we know one point on the graph now, which is this y-intercept. Now x-intercept is actually pretty easy in this case too, because we have it factored and we have it in lowest terms. The x-intercept, remember, we want the numerator in lowest terms to be equal to 0. So all it simply is x minus 7 equal to 0. Add 7, x equals 7. So our y-intercept is 7, 0. So if we look at the graph, let's see if the graph agrees with a lot of this stuff. So an x-intercept is 7, 0. It agrees. A y-intercept of 0, negative 7, 6. 7 over 6 is 1.1666 repeating, so that's true. Does it have a hole at 3 and negative 1/3? Well, it appears that would fit the pattern. And if you look at our table over here, when I look at 3, I again put negative 3, which is the other problem in the domain. But if you type in 3 in your table, so I'd put a 3 in your table and it should tell you another undefined. So hopefully this is a pretty comprehensive review of how to find the intercepts and holes. Again, we did use our graphing calculator a lot to check our work, and I would encourage you to do that as you try these problems.